Hello, welcome everyone. In this video, we are trying to understand how the differential piston area pump works. So, it is made up of two pistons. This is the bigger piston, and I'm not very good at sketches, so please forgive me, pardon my sketches. This is the smaller piston. The diameter of the bigger piston is D1, the diameter of the smaller piston is D2. What we are trying to understand in this case is the construction, the working principle, and how the nominal pressure ratio is derived. Okay, so this is my piston. Let's hatch this, and these two are sealed off from each other because these are handling different fluids. Sorry, this should be cross hatched, and these are reciprocating in their own cylinders. Okay, so I'm assuming in this case that this is a pneumatic pump, and that is why uh, the pressure of air acting on the driving piston is P1, and the pressure of air acting on the driven piston is, sorry, the arrow should be the other way, discharge should be P2. Okay, now let's try to understand what happens when I'm applying this pressure P1. The air pressure is acting on this bigger piston. The force that is exerted, the force that is experienced by the bigger piston is P1 times A1, that is P1 into pi d1 square upon 4. d1 is the diameter of the bigger piston. Now this force is transmitted to the smaller piston because we are assuming, or you can theoretically say, that this piston rod is rigid. So F2 that is experienced is P2 times A2. Okay, F2 is equal to F1 because, just as I just mentioned, that the piston rod is rigid. So now let's try to understand pi. What I've written here is F2 is equal to F1. So what that makes it is, let's try to substitute this in this equation. So you can call this as equation 1, this is as equation 2. So let's try to substitute, uh, sorry, let's try to make it this as 2 and this as 3. Okay, let's try to substitute 1 in 3 first. So what that makes it is F2 is equal to P1 times pi d1 squared upon 4. Okay, now this is equal to F1. Okay, and that is equal to P2 times A2. Okay, so that is equal to P2 times pi d2 squared upon 4 d2. Okay, so F2 is equal to F1. So from that I'm getting this is P1 times pi d1 square upon 4 is equal to P2 times pi d2 square upon 4. Okay, so let's write that down. P1 times pi d1 squared upon 4, okay, is equal to P2 pi d2 squared upon 4, right? So what I'm trying to derive in this case is the nominal pressure ratio. Nominal pressure ratio is given by P2 upon P1 will be equal to, you can see P2, if I move it here, what will happen is pi P2 upon P1, so pi d1 square upon 4, pi d1 squared upon 4 upon pi d2 squared upon 4. We can cancel this this and this, so that comes to d1 square upon d2 square, that is equal to, that can also be written as d1 upon d2 the whole square. What this simply means is the pressure ratio will be the square of the ratio of the diameter of the two pistons. So what this simply means is, if I have a driving piston which is the driven piston. So see, if I have a driven piston of diameter say 1 centimeter, okay, and a driving piston which is say 6 centimeters, then my nominal pressure ratio will come out to 6 upon 1 the whole square. That is, this is simple mathematics, that is equal to 36. It simply means my pressure will be, if I am supplying pressure, if the operating air pressure is 1 bar, I'll get, this will be transformed to a pressure of 36 bar on the driven fluid. You can consider this as water or maybe any other gas even can be handled using this. In that case, it will be called as a compressor. So now what in many of a small observation or a small point I would like to add, this pump is many a times considered to be operating on the Pascal's law. People say, I've heard people saying that this is operating on the principle of Pascal's law, but this pump is not operating on the principle of Pascal's law. I'll make a video on that too and explain to you why it cannot be considered to be working on the Pascal's law. So that's all in this case. Thank you so much.